In mathematics, a product is the result of multiplying, or an expression that identifies factors to be multiplied. Thus, for instance, 6 is the product of 2 and 3, and is the product of and. The order in which real or complex numbers are multiplied has no bearing on the product. This is known as the commutative law of multiplication. When matrices or members of various other associative algebras are multiplied, the product usually depends on the order of the factors. Matrix multiplication, for example, and multiplication in other algebras is in general non-commutative. Product of two numbers, product of two natural numbers. Placing several stones into a rectangular pattern with rows and columns gives stones. Product of two integers, integers allow positive and negative numbers. The two numbers are multiplied just like natural numbers, except we need an additional rule for the signs. In words, we have minus times minus gives plus, minus times plus gives minus, plus times minus gives minus, plus times plus gives plus. Product of two fractions can be multiplied by multiplying their numerators and denominators. Product of two real numbers. The rigorous definition of the product of two real numbers is too complicated for this article. But the idea is that one takes a decimal approximation to each real and multiplies the approximations together, and then take better and better approximations. Product of two complex numbers. Two complex numbers can be multiplied by the distributive law on the fact that, as follows. Geometric meaning of complex multiplication. Complex numbers can be written in polar coordinates. Furthermore, from which we obtain. The geometric meaning is that we multiply the magnitudes and add the angles. Product of two quaternions. The product of two quaternions can be found in the article on quaternions. However, it is interesting to note that in this case, and are different. Product of sequences. The product operator for the product of a sequence is denoted by the capital Greek letter pi. The product of a sequence consisting of only one number is just that number itself. The product of no factors at all is known as the empty product, and is equal to 1. Further examples for commutative rings, residue classes of integers, residue classes in the rings can be added and multiplied. Rings of functions. Functions to the real numbers can be added or multiplied by adding or multiplying their outputs. Convolution. Two functions from the reals to itself can be multiplied in another way, called the convolution. If then the integral is well defined and is called the convolution. Under the Fourier transform, convolution becomes multiplication. Polynomial rings. The product of two polynomials is given by the following. With products in linear algebra, scalar multiplication, by the very definition of a vector space, one can form the product of any scalar with any vector, giving a map. Scalar product. A scalar product is a bilinear map. With the following conditions, that for all. From the scalar product, one can define a norm by letting. The scalar product also allows one to define an angle between two vectors. In dimensional Euclidean space, the standard scalar product is given by cross product in three-dimensional space. The cross product of two vectors in three dimensions is a vector perpendicular to the two factors, with length equal to the area of the parallelogram spanned by the two factors. The cross product can also be expressed as the formal determinant. Composition of linear mappings. A linear mapping can be defined as a function f between two vector spaces V and W with underlying field f, satisfying. If one only considers finite-dimensional vector spaces, then in which BV and BW denote the bases of V and W, and Vi denotes the component of V on BV, and Einstein's summation convention is applied. Now we consider the composition of two linear mappings between finite-dimensional vector spaces. Let the linear mapping F map V to W, and let the linear mapping G map W to U. Then one can get, or in matrix form, in which the I row, J column element of F, denoted by Fitch, is E, and Gij equals G. The composition of more than two linear mappings can be similarly represented by a chain of matrix multiplication. Product of two matrices, given two matrices, and their product is given by. Composition of linear functions is matrix product. There is a relationship between the composition of linear functions and the product of two matrices. To see this, let R equals dim, U, S equals dim, V, and T equals dim, W, be the dimensions of vector spaces U, V on W. Let be a basis von U, be a basis of V on be a basis of W. In terms of this basis, let be the matrix representing phi U of V and be the matrix representing GAR via W. Then, is the matrix representing. In other words, the matrix product is the description in coordinates of the composition of linear functions. Tensor product of vector spaces, given two finite-dimensional vector spaces V and W, the tensor product of them can be defined as a tensor satisfying. Where V and W denote the dual spaces of V and W, set theoretical product. In set theory, a Cartesian product is a mathematical operation which returns a set from multiple sets. That is, for sets A and B, the Cartesian product A, B is the set of all ordered pairs where A and B are B, empty product. The empty product is the value of 1 just like the empty sum has the value of 0. Products in category theory. It is often possible to form the product of two mathematical objects to form another object of the same kind. Such products are generically called internal products, as they can be described by the generic notion of a monoidal category. Examples include, the Cartesian product of sets, the product of groups, and also the semi-direct product, knit product and wreath product, the free product of groups, the product of rings, the product of ideals, the product of topological spaces, the Wick product of random variables. The cup and slant product in algebraic topology. The smash product and wedge sum in homotopy. For the general treatment of the concept of a product, see product, which describes how to combine two objects of some kind to create an object, possibly of a different kind. But also, in category theory, one has, the fiber product or pullback, the product category, a category that is the product of categories. The ultra product, in model theory. Other products, Hadamard product, Kronecker product. The product of tensors, wedge product or exterior product, interior product, outer product, tensor product. A function's product integral. The product integral is also known as continuous product, or multiplical. Complex multiplication, a theory of elliptic curves. See also, pi, iterated binary operation, notes. References. External links, product on Wolfram Maths World, product at planetmath.org,